In this video, we are going to prove a lower bound on the genus of y, which will serve us, I mean, it's interesting and it's all right, but it will serve us as a way of proving the main theorem of this lecture, which is that, X is connected. Quite modest, but nonetheless non-trivial. Right, so as I said, we are going to start by proving that the genus of ypq is very large, 2 log q to the base p. So right, let's just shorten this graph of the graph by g, and let's consider a cycle which achieves this graph, namely a cycle, a simple cycle, x0, x1, up to xg minus 1 xg, which is back x0. And this is a cycle in y, right? Right, the vertices of y are elements in this group, just to remind you. And because this is a Cayley graph, as we argued before, you can use vertex transitivity and kind of shift that cycle to a cycle which starts and ends with 1. So let's assume that x0 and xg are simply 1, namely 1 as an element of this group. And this is a Cayley graph with generator set capital T, TPQ, but I'll stop saying that P and Q all the time. So let's consider the generators that lead us through this cycle. So xi is the product from T1 up to Ti. Right now, Ti are elements in TPQ. And TPQ, recall, is you took SP, the P plus 1 primes that we, quaternions, integral quaternions that we like, and we reduce them according to the relationship, to the equivalence relation Q, and then according to pi q, which descends tau q. Let me remind you of that. Right, so TPQ sits here. You start from SP, you apply capital Q. This is the weird, equivalence relation that comes from the unit factorization, and then we did pi q, right, which if you remember, essentially, okay, so many stuff going on, which essentially take you, it's a reduction, okay, yeah, that's the best way of saying that. It's the reduction of tau q down to the quotient groups. Anyhow, but elements in TPQ sits here. Okay. So let's consider the corresponding G elements in SP, gamma 1 up to gamma G, to be those unique elements that gives you the T's, right? So Ti is obtained by applying pi q on gamma I. Okay, or if you want, pi q on q of gamma I, which is just the class of gamma I. Okay, so we have the excess, we have the gammas that generates them, and we have the T's that underlie those gammas. And now I want to look at the product of the gamma i's from 1 to g. So let's consider the product gamma 1 up to gamma g. Right, this is at the level of SP elements, right? So let's denote this thing by alpha, and this thing is an element in lambda prime, right? So the gammas are coming from SP. A product of things in SP is not going to be necessarily in SP. These are just, it's not going to be in SP because each of them has norm P, and so a product has norm P squared, cube, and so forth. But they are all going to be in lambda prime, where recall lambda prime is this, right, initially, is, those quaternions, integral quaternions, whose norm is a power of P, so that's fine. A product gives you a power of P. And you have this either one, you have this, parity thing going on. Either the coefficient, the constant coefficient is odd, sorry, either the non-constant, the imaginary coefficients are even, or the constant coefficient is even. Right, and if you think about it, when you multiply those, you get something like, I mean, we already know that because we know even quotient by tilde gives you a group, but this is when you take the products of things from SP or from lambda prime, you're staying in lambda prime. Yeah, sorry, that was, we already know that anyhow. But I'm just kind of saying why these gamma i's sits in lambda prime. On the other hand, let's write alpha as, as you can write any integral quaternion. And the first thing to note is that alpha is a reduced word over SP. That's because the cycle is simple. And we had this before. And if the cycle, if it's not a reduced word, namely you have either a beta squared, the beta coming from SP, or alpha and alpha conjugate, or vice versa, then that would correspond to a cycle in which you go back and forth, which won't be simple and therefore won't attain the graph. So alpha is a reduced word over SP, and the class of alpha, which is just the class of the gamma, the product of the gammas, can't be the same as the class of 1, right? Because then that would contradict the unique factorization, right? Because this is a reduced word, and 1 is another reduced word. And like G is at least 3. So they are not equivalent. Good. So this means that alpha is not equivalent to 1, namely at least to. So what I'm claiming is that from here, that at least one of the imaginary coefficients, A1, A2, or A3 is non-zero. Okay, because let's assume that all of them are 0, then the norm of alpha, well, it's a power of p, just because alpha is in lambda prime. But if all of these coefficients are 0, then alpha is just A0. And so the fact that just a number, integer. And so the fact that the norm is a power of p means that that integer is, up to maybe plus minus, is a power of p. And that is equivalent to 1, in contradiction to the fact that we know that alpha is not equivalent to 1. Okay? So from all of these things, we know that we know something about the product of the gamma i's, gamma 1 up to gamma g. We know that it has an imaginary part, right? On the other hand, let's look at pi q of the class of alpha. Well, that's just the product of the ti's, right? Because alpha is gamma 1 up to gamma g, if I remember correctly. And so the class of alpha is the class of gamma 1 up to gamma g, which is just the class of gamma 1 times gamma g, which is just T1 up to Tg. Okay? So on the other hand, let's look at pi q of the class of alpha, which is just the product of the Ti's, right? Because we know that alpha itself is gamma 1 up to gamma g. So the class of alpha is the class of gamma 1 up to gamma g. And so if you apply pi q on the left-hand side, you get pi q on the right-hand side. And it's an homomorphism, and this is, you can write it like that also. So you apply pi q to each of the terms. And that's the definition of T, right? T is pi q of gamma, this thing here. Okay, just definitions, but a lot of definitions. Right, so we know that pi q of the class of alpha is the product of the TGs, but the product of the TGs is, leads you to the last vertex, xg, which is 1, right, as an element in the quotient. And so from that, we know that this element sits in the kernel of pi q, which we denoted by lambda q. And actually, we understand lambda q, right? Lambda q, by a previous claim from the previous video, tells you that q divides all of the imaginary parts. But we know from before, from just what we did now, that one of them is non-zero as an integer. So one of them is a non-zero multiple of q. Okay, at least one of the i's 1, 2, or 3, is at least q in absolute value. And so this means that if you're going to look at the norm of alpha, which by definition is this thing, well, on one hand, it's at least q squared, because one of these is q, at least, it's divisible by q and non-zero. And on the other hand, the norm of alpha, well, alpha is just a product of the gamma g's, the gamma i's, and all of them are in SP, has no p. So the norm of alpha is p to the g, just the product. And that's it. From here, you can see immediately that g is at least 2 log q to the base p. Right, so the norm kind of captures the length of the path. And because it's in a quotient group, it must be large enough, and so forth. Okay. Good. So anyhow, what we just proved is that the girth of this graph is quite huge. Actually, it's really huge. It's 2 log q to the base p, and it's not hard to show. It's something that you can do. We did, or at least said at the first chapter, is that it's easy to show that if you have a k-regular graph, kind of generally speaking, just a simple counting argument, maybe k is at least 5 to make it clean, then the girth of the graph is at most essentially 2 log number of vertices to the base degree minus 1. That's really just because you start from a vertex and you visit like, k neighbors, and from there you visit at most k minus 1 new neighbors, not including the previous one. That's why you have the k minus 1 here. And then proceeding like that, and by some argument like that, if the graph was larger than that, then you would have visited too many vertices. You can check it out. So the graph, it can be at most this thing. Yeah, so you can compare it to the bound, but actually I want to do something else. So you can do this, and on the other hand, so in our particular case, g of our graph is at most 2 plus 2 log p, because the degree is p plus 1, of the size of the graph. By that I mean the number of vertices, by the way. That's the name of the graph. So I mean the number of vertices, which is just the size of this quotient group. And if you use what we proved just now, the lower bound, which is, let's see, 2 log to the base p of q, then, right, you can see that, so if you take pth power, then you get that q squared is at most pth power. Okay, let's see if I can do it. So you have a p squared times the size of the graph squared. Okay, and you can remove the squares. I could have done it before, actually. And from this, you can see that the size of the graph, number of vertices, is at least q over p. And we will need that. Okay, so we will need both that the graph is somewhat large, and using that also the fact that the graph is not too small. Okay, other than that, we won't care about the graph anymore. Okay, so already finally to prove the main theorem of this lecture, which tells the following. It says that assume p is at least 5. I think I also need the fact, because I'm under this assumption that p congruents to 1 mod 4. Q is sufficiently large, p to the 8, you'll see why. And that p is a square modulo q. Okay. You can also work with p equals equivalent to 3 modulo 4, and when p is not a square modulo q, but let's keep things simple. Then what I'm saying is that xpq is connected. That's what we wanted to prove here. And in particular, because we know that ypq is a connected component of xpq, that would imply that they are the same graph, they are isomorphic. So what does it mean for a Cayley graph to be connected? It means that the generating set literally generates the entire group. So we need to show that SPQ generates PSL2Q. And we know already that TPQ generates lambda over lambda Q. We know that Y as a Cayley graph is connected because it's the quotient of a tree. So let me go to the picture, and maybe it's quite ugly at this point, but right. So we know that TPQ, so sitting here, TPQ generates Y. Let's just call it T. T generates Y, and we want to show that S generates X. And we know that beta takes t to s, right? So t goes to s, and we know that t generates y, and we want to show that s generates x. I'm kind of inventing this notation here. So, right, so for that, what you really need to show is that beta takes y to x, right? Because then you can kind of push the generators from t to s, right? So every element in y is generated by t, and so every element in x, you can go back to the corresponding element in y, check who generated, and use beta to find the s generators for the corresponding element. So that's what's written here. So all we need to show is that beta of the vertex set of y is PSL2Q. And for that, we're going to use like a big hammer that we proved. So if you remember, we had this theorem that tells you that if Q is a prime and H is a proper subgroup of PSL2Q, which is sufficiently large, then H is meta-abelian. Okay, and there was a definition for meta-abelian, but I'm going to give you an equivalent definition here that will be useful for us. So even if you don't remember the definition, that's fine. So an abelian group, you can state it in terms of the commutators, and you can say that a group is abelian if and only if the commutator of every two elements is 1. Right? Because this is G inverse H inverse. And say it's abelian is just saying that the commutator is always 1. A group G is meta-abelian if it's not that the commutator of every two elements is 1, it's that for every 4 elements, the commutator of the commutators is 1. It's actually a good exercise that we should have done already then. But right, so a group is meta-abelian if you have that. And the theorem, that's not so hard to get from the actual definition, so you can try to do that, prove the if and only if. Like not the actual definition, that's also definition, but the definition we used to prove the theorem above. And the theorem above tells you that no proper subgroup, sufficiently large proper subgroup of PSL2Q is a meta-abelian. Sorry, every large subgroup of PSL2Q which is proper is meta-abelian. Good, yeah. Good. So let's set HPQ to be this intersection of two groups, so PSL2Q, and the image of this group under beta. Okay, so by this theorem that I just quoted, we need to show two things. We need to show that HPQ is at least of size 60, because the theorem requires the groups that you're looking at to be of size larger than 60, and that HPQ is not meta-abelian, right? Because the theorem tells you that if you are looking at a subgroup of size more than 60, then it's always meta-abelian unless it's not proper. And that's a way of proving that indeed what you're looking at is the entire PSL2Q. Okay, so we are going to show it's at least 60 and it's not meta-abelian. So why is it of size at least 60? Well, we know that we assume that Q is at least P to the power 8 and P is at least 5. And by the previous remark, where we bounded the number of vertices of Y, we know that it's at least Q over P. And if you plug in the parameters, you'll get that this is a number which is more than 120. And you might expect to see a 60, but it's 120. And the point here is that HPQ is the intersection of PSL2Q and this thing which we know is of size at least 120. And PSL2Q has index 2 in PGL2Q. So at least one part, so this part has to be of size because it's symmetric. Every size has to be of size at least 60. So HPQ is of size at least 60 or more than 60. Now, why isn't it meta-abelian? Well, here, because of this characterization, we just need to find 4 elements G1, G2, G3, G4 in HPQ, whose commutator of commutators is not 1. And the way to do so is to just do the following. I mean, you can do it in several ways, but take G1 and G3 to be anything you want, but equal. And make sure that when you choose G2, it's not G1 or its inverse. And G4 is not G1 or its inverse, and not G2 or its inverse. And by this choice, if you're going to just write this commutator, right? So it's like, wow. Okay, so I'm just going to start just to show you what's going on. This is G1, G2, G1 inverse, G2 inverse. And this is G3, G4, G3 inverse, G4 inverse. And now I need to write this and that, and this inverse and that inverse. Anyhow, we get a word of length 16. And it's a reduced word because you made sure there are no cancellations between consecutive elements. Okay, so you find a reduced word of size 16. And by the proposition that we had about the GIRF, I told you we'll need it one more time. We know that the GIRF is larger than 16, right? Because it's at least 2 log to the base P of Q, and Q is at least P to the 8. So this is larger than 8. It's larger than P to the 8. So this is larger than 8. This is larger than 16. So this means that this word cannot be 1. It's a reduced word. It cannot be 1. It's too short. It's too short to kind of close the cycle, which is what we wanted. Good. So to summarize, we have the following corollary. So assuming that Q is larger than P to the 8th, P is congruent to 1 mod 4, at least 5, and a square modulo Q, then X is a P plus 1 regular connected graph. That's what all we need from here on. But, we already took the trouble to prove that the graph is large, and so the graph is large. It's at least this number. I mean, we said that it's at least 2 to log to the base P of Q, but it's nice actually to write the graph in terms of the graph size. And the graph size is not Q, it's this thing. And if you remember, we actually computed the size of the vertex set of XPQ. It's most Q cubed, and therefore when you plug it, you get this 1/3 here. Okay, good. So next time, it's going to be next week, I'm going to start talking about the expansion of X, not just its connectivity property.